All right, welcome everyone to another Wolfram Institute seminar. Today I am pleased to introduce Pavel Hajek. I am very happy to be introducing this topic today. Um, he's going to tell us about hypergraphs and Lie brackets. So some of you might know, some of you might not know, but my background is in Lie geometry. My initial interest was in the mathematics of classical and quantum mechanics. So I got intimate with Poisson brackets and Lie algebroids and Lie groupoids and all these kinds of things. So when a few years ago I switched gears and got into this hypergraph business that eventually led me to work with this fine folks here in the Wolfram Institute, I thought, okay, I'm done with Lie brackets. You know, this is a thing of the past. And then Pavel came around and said, "Hey, I've been working on this stuff. I'd love to mix these two things." And I got introduced also from other institute affiliates to this Lie bracket insertion algebras and things like that. And you know, we got going with our winter school project. And so I'm very happy today to have Pavel present these ideas. I hope that we can get a nice overview and also some time for discussion and brainstorming, because unfortunately, when Pavel was first doing this project, I was very busy with something else that got 98% of my attention. So I'm eager to revisit these ideas and discuss them again. So please, Pavel, floor is yours.
Hi, hello. Thank you very much. Thank you very much, Carlos, for the introduction. So I have to share my screen. Yeah, give me a second. Now. Good. So my talk is called Lie bracket on hypergraphs. And right. Okay, good. So first, I need to clarify the terminology a little bit. So we are going to consider Lie brackets on the vector space generated by isomorphism classes of hypergraphs, which are based on the operation of inserting one hypergraph into another hypergraph at a single vertex or an edge. We are not going to be considering any Lie brackets on vector fields on a fixed hypergraph as in infrageometry. So these are two basically places where you could think about finding hypergraphs. The second is from infrageometry. It is based on viewing a hypergraph as a model of some discrete space, considering vector fields on that. And as it is known from differential geometry, vector fields have natural Lie brackets, the commutator of vector fields. But we are going to consider different situation. In our case, we are basically we are going to be computing Lie brackets between linear combinations of hypergraphs. Yeah. So that's the question. So as you may know, so these Lie brackets on a manifold. So in the second case, they correspond to infinitesimal generators of some diffeomorphism of one parametric diffeomorphism of the manifold. And what it corresponds to in this case, this is a question for discussion. So this should be enough for the clarification. Now, what's the source of the ideas is basically my Wolfram community post based on my work for the Wolfram Winter School 2025. And there I think I kind of did a lot, introduced kind of lot of ideas, not everything very precise, but anyway, if you want to see like an overview of all the ideas which I got during the 2 weeks, you can have a look in that. So what I did there, I defined insertion Lie bracket on rooted hypergraphs. I basically explored its relation to the commutator of certain hypergraph rewriting rules. Having a Lie bracket, you can extend the Lie bracket to a Poisson bracket of formal functions on the basically moduli space of hypergraphs. And then I also defined a generalization because this insertion Lie bracket is inserting one is based on the operation of inserting one hypergraph with a root. So the root is a vertex. By gluing this to another vertex to a vertex of another hypergraph. And you can generalize it because in the case of hypergraphs, you can consider root n edge. So you have one tucked n edge, and you identify it with you glue it to an n edge in the target hypergraph. So this is basically this generalization. It also gives you Lie brackets. Then I was thinking about how to kind of motivate, how to detect Jacobi identity or some relations. Basically from the corresponding multi-way systems. Then I kind of introduced the notion of sign confluence. And then I was thinking about higher order brackets and higher order relations and so on. So this is a source of ideas. But the today's goal is actually to introduce you, to show you my recent progress, which is an implementation of a graded insertion multi-bracket on vertex ordered hypergraphs. This is in a way native operation on Wolfram Institute hypergraphs, and this is what I'm gonna basically, what I can now present you fully, the full construction of that. And the same construction can be applied to construct the other, can be taken as a base to construct the other Lie brackets. What are my immediate next steps? So I basically want to test it and eventually merge it in the Wolfram Institute hypergraph package. And then after that, I will implement this insertion multi-bracket on hypergraphs with tucked and edge. So that's my immediate next steps. Are there any questions to this? So if there are no questions, then I will move to the next slide. How to move to the next slide? Yes. So for those of you who are seeing hypergraphs for the first time, so hypergraphs are natural generalization of graphs that allow n edges, which are edges that consist of n vertices for each n. Yeah. A special case of these hypergraphs, which are kind of nice to visualize, are the so-called simple hypergraphs, where no edge contains a single vertex multiple times. So edges are subsets, and edges are subsets of n elements with n elements of the set of vertices. To see some example, I'm using basically here the Wolfram Institute hypergraph booklet by Carlos and Nick, and they have this function random hypergraph, which can generate you a random simple hypergraph with three 2 edges and one 5 edge. Yeah. So this is how hypergraph looks like. You can also, I'm having some convenience function where you can basically also it gives you some random simple hypergraphs by specifying some max edge count and so on. This is just convenience function for my experiments. But anyway, these are hypergraphs. And now what hypergraphs, you can actually see hypergraphs appearing in real life, so to say. For instance, by representing n-array relations. You can actually also see hypergraphs, recently hypergraphs actually appearing in even software engineering, because there are hypergraph database models, which are, you can view as simple database model as a table, which is a binary relation, but hypergraphs are basically n-array relations, so like multi-dimensional tables. So, and that's a nice example of an n-array relation, which it can represent is, for instance, connectedness of linkedness of unnodes. So these are trivial nodes, and basically they can represent the relation of being linked together. In this picture, you see that each two of these unnodes, they are linked together. So that's why there is a 2 edge between each pair of vertices. Whereas on this picture on the right, none two unnodes are linked, yeah, but all three are linked together. You cannot separate them. So this relation would be represented by this hypergraph with single 3 edge.
So just for clarity, that is to say, if you took away the green,
What?
ring on the one on the left, the red and the blue would still be linked.
it's still the green is linked with the blue
And the red.
and the red. Yeah.
Uh-huh.
So the green has edges from both to the red and to the blue.
But if you took away any one of them, the other two would still be linked
Yeah,
together.
they are still going to be linked together. Yeah. So yes,
Yeah.
yes. It's like
That's exactly the point of the ternary link there. That if you remove any of the three,
yeah.
the link disappears. But in the other one, if you remove any of the three, the link remains. Right. So
Yes, that none two of these are linked,
Yep.
which basically say that if you remove one, then the rest is not going to be linked. Yeah, so this is like a motivation for hypergraphs.
Yeah.
Now let me go to the next slide.
One quick question, Pavel. Just a technical clarification. Moving forward, you're gonna focus on simple and directed hypergraphs. Is that right?
No. I'm gonna focus on general hypergraph. It's not really. I'm not really considering edge orientations currently.
So undirected.
Undirected hypergraphs. Yes.
Yes. Okay. Simple undirected, right?
Not necessarily. Although simple is a question, I would say rather let's restrict to simple and undirected hypergraphs. So
Yeah.
let's restrict to simple and undirected
Yeah.
hypergraph. For those who are seeing it for the first time, undirected is about having an orientation on the vertices in each edge, which we are now saying all edges, no edge has orientation, so all edges can be mapped on each other by any permutation. Good. So now, what is the graded vertex insertion bracket? So now it's a bit of mathematical formulation. So I'm going to construct a multilinear bracket. So it will have n inputs, and to each input, you can basically plug in a linear combination of hypergraphs. And this bracket is going to be linear in each input. There is going to be some degree, which I will define on the hypergraphs, and this bracket is going to preserve the degree. So the degree of the multi-bracket is going to be the sum of the degrees of each of the inputs. And this bracket, this multi-bracket, is going to be given as a total anti-symmetrization of the insertion operator. So just spoiler for the future slides. So the insertion operator on n graphs is basically taking the rightmost graph, takes its root, and it's inserting the root into the previous graphs. On each step obtaining another rooted graph and inserting it to the previous one. And it's doing in all possible ways. And this bracket is just anti-symmetrization with respect of anti-symmetrization of this operator with respect to the inputs. And this plus minus is the so-called causal sign. I will explain later what it means. And finally, the degree is the shifted vertex degree, or maybe shifted, I forgot the correct word, suspended vertex degree. So it's the vertex count -1. You can actually just check that this equation holds, because you see that on the, I told you that the bracket is going to be basically insertion of the brackets in each other. So here you are going to have in total n minus 1 insertions. Yeah, so you are going to lose here n minus 1 degree, plus degree is taking the so here's going to be vertex count of this is going to be n minus, so the vertex count of the sum minus n minus 1, because you lost n minus 1 vertices during the gluing. And then to get the degree you have to subtract 1, so it's going to be like minus n, and so it's going to be the vertex count minus n, which is precisely what you are getting on the right hand side. So you see that the degree relation holds. what is good on this bracket, that it actually works directly with Wolfram Institute's hypergraphs as they are defined when you see them as vertex ordered hypergraphs. So basically, this Wolfram Institute's hypergraphs are defined as some sort of data structure, and basically, if you consider different, you can consider this hypergraph up to different isomorphism, and this bracket is going to be defined on these hypergraphs, which are on the isomorphism classes of these hypergraphs as vertex ordered hypergraphs. That means that your vertices are basically labeled from 1 to n. So it's a very, very simple. There is not that many isomorphism. It's really, you just have to have a look at, you just can check in linear time if two hypergraphs are isomorphic. So this is just, yes, and it turns out that for n equals 2, this is a graded Lie bracket, which I can prove. And in the way I'm going to construct it, you can use the same construction and specialize it to actually isomorphism classes of rooted graphs, rooted hypergraphs, where the isomorphisms are not anymore trivial. And this specialization for n equals 2 gives a generalization of the insertion Lie bracket for rooted graphs from this paper. Basically, my work for the Wolfram Winter School is a generalization of constructions in this paper to hypergraphs, and all these generalizations to tucked and edge and so on.
So can you elaborate somewhat on what rooted means in this context?
So what rooted means? So rooted means that you have basically one chosen vertex in the hypergraph. We will see the examples later. I hope I already initialized everything. I can maybe define some hypergraph here, 1, 2, 3, and I can make root red, and I can also label the vertices. Yes, and rooted hypergraph means that there is one chosen vertex. So it basically corresponds. Rooted hypergraphs corresponds to such pictures. Yeah, and the isomorphism is basically identifying two hypergraphs by mapping the red vertex to red vertex, and the rest by any permutation which preserves the hyper edges. So this would be rooted hypergraph, and this would be vertex ordered hypergraphs. Yeah. So this one is vertex ordered, and this one is rooted. And on this vertex ordered, you are having the graded Lie bracket, and on this rooted, you are having a classical Lie bracket, and it's on the isomorphism classes of hypergraphs as rooted hypergraphs, and this is on the isomorphism classes of vertex ordered hypergraphs as of hypergraphs as vertex ordered hypergraphs. Is it now more clear?
Yes, thank you.
Okay, good. So let me move to. In order to define these creatures, I have to show you how I do basically graded multilinear algebra in Wolfram language. I am not sure if there is some kind of package for that or something like that, but I basically implemented everything myself. So basically, we are going to consider, as I told you, inputs of these brackets are going to be vectors of hypergraphs. And these vectors I'm representing as associations. Where on the left hand side you have the hypergraph, and here you have the coefficient. Yeah.
And the coefficients are going to be rational by default or real or
actually, so the brackets are with z coefficients.
sure, makes sense.
Yeah, so you cannot get anything else. You can restrict to z coefficients, and the brackets are preserving the And the results of the brackets are going to also have z coefficients.
What,
Good.
so z coefficients, z coefficients are
Yeah, sorry, z coefficients, like integer coefficients.
integers. So what's being associated here with the 0.91?
Yes, so here are just being associated reals. I did not define any coefficients. I can also define here. I need to check out how I implemented this random simple hypergraph. There is coefficients is now set to random real, so I can also define the function coefficients as let's say random integer, right? Random integer 5 and like this, and it should give random integers. Is it doing something? Did I do anything wrong? Give me a sec. It's computing. See, now it is there. Now it has random integer. Yeah. Interestingly, the random integer, yes. Interestingly, the random integer is the same for each. So maybe the coefficient function. Because I have to map it somehow like this. And here I have to invoke each time the random integer function, right? Yes. But I think that at this point, this is not like crucial. At this point, we understand that the brackets are with integer coefficients. Yes.
Yeah.
You can of course you can feed them with real coefficients. Nothing will happen, but you will also get out real coefficients. I don't know why these random hypergraphs functions are taking so long.
I think you still need to specify the maximum integer range. So.
Maximum. Okay. I need to. Okay. And maximum integer range. Let me specify to be, I don't know, 10. Is it doing something? Yeah, but I think that I think that this is hanging on the random hypergraph, because maybe I want too much from the random. Yes, now it is. See, now we generated a random vertex with integer coefficient with three elements, and with of hypergraphs which should have maximally five vertices. Good. And now another notion which I will use is the notion of multilinear extension. So basically, if you have a function f, I will want to extend it to a multilinear function. So if big F, which is a function which I can feed with associations as inputs, and it will distribute the function small f in a multilinear way. Yeah, so I can, if I run this code, then you see that basically it distributed the result is the small function f distributed over all these tuples from the inputs with the corresponding coefficients obtained by multiplication. Yeah. So this is a multilinear extension. Next thing, what I will explain is the so-called causal sign. And causal sign is defined, or causal sign maybe, is defined as the aggregated sign of a transformation of symbols a1 up to an to a sigma 1 up to a sigma n, where sigma is a permutation, under the supersymmetric commutation relations. So possible supersymmetric commutation relations can, in their generality, look like this. So it's basically when you have two neighboring elements, then you get a sign by commuting them, which depends on some given parity and on the degrees of the symbols in this way. And causal sign is if you are given a permutation of these symbols basically you choose some way how to sort them from the permutation to the order 1 to n, and you aggregate the sign. You collect the sign from every transposition. So that's causal sign, and basically for the permutation 2, 3, 1 of elements with degrees 1, 0, 1, and if I take parity 1, then you obtain -1. Why do you obtain -1? Because you have to permute this 1. You have to permute it to the front, which means that you do two transpositions. Each of them is giving you, because we have parity 1, each of them is giving you sign -1, so it is canceling. So from the permutation part, you are getting just 1. But here the degrees, the element 1 is having degree 1, element 2 is having degree 0, and element 3 is having degree 1. So you are getting an additional sign from this term when you are permuting element 1 over element 3. So in this permutation, you are getting minus. That's why it's minus. Actually, when I was writing this talk, I realized that this can be illustrated as a multi-way system. Because actually it's not clear if you define causal sign like this, it's not clear that the definition does not depend on the way how you sort your permutation. So basically the fact that this causal sign does not depend on the way you sort your permutation is equivalent to confluence of the causal multi-way system, which I will just show. Wait, I'll wait until it generates something nice. Yes, for instance, is it nice, or maybe I can even better. I want something with signs. Wait, let me. Yes, for instance, here now it looks nice. Yeah. So basically, you generate some random permutation, which is in this case. You generate some random assignment of degrees to your elements. You generate some random parity. Parity is in this case 0. And then you go on and you are applying in your multi-way system, you are applying the rules which are basically just the flipping rules. If j is bigger than I, then you flip them. Okay? And basically, if you apply these rules in all possible way, and you are keeping track of the sign, which is here this red thing, you are getting confluence in the end. And this confluence is equivalent to the fact that the causal sign is well defined. This is some
Very
kind of
nice.
fun effect. Yeah.
Yeah, that's super cool to see
Yeah.
in that explicit way.
And I because the code of the multi-way system is kind of hard to understand, I did not manage to plot the events. So if somebody wants to help me, if somebody thinks it's a cool illustration of this phenomenon and wants to help me plot the events, somebody would have to explain me how to define all these functions for the multi-way system. Yeah.
Very nice.
Good. So, and the last thing what we will need when we have causal sign, we will need also symmetrization, graded symmetrization. So again, we are taking this total symmetrization. Let's call it total symmetrization, and you are taking a function small g, and you want the function g to be basically as I was defining on the previous slide, the sum over all permutation with the causal sign. So it's going to be a vector of small g applied to all permutations with the corresponding sign.
Pavel, can we zoom in a bit so we can see better?
Yeah, that's good. It was a bit zoomed out moments ago. Great.
Also, just to point, your video is blurry. I don't know if there's anything you can do about
that.
You mean my screen sharing or my video?
No, your the video of your face, your actual video.
That's fine. You can watch the screen sharing. No, I'm not. I don't know if I can do anything with that currently. Actually,
Okay, that's
I'm
fine.
not
No
seeing.
worries.
I'm not seeing anything, and yeah.
Okay.
I'm sorry for being a little
Thank you for zooming in.
Good. So this is the last ingredient which we need to construct our operations. And now, finally, construction of the graded vertex insertion multi-bracket. And now having all these ingredients, actually, it's very easy. So the vertex ordered insertion bracket is defined as the multilinear extension of the symmetrization of the vertex ordered insertion operator using the shifted vertex degree. Shifted vertex degree is this vertex count -1. This is what I defined on the T vertical slide. And vertex ordered insertion is precisely the operator which is inserting this n tuple of hypergraphs into each another to each another, like forming like a chain of these hypergraphs. There is one technical step, because I told you that we are working up to isomorphism. So at some point we have to collect isomorphic hypergraphs, which we are doing by applying this function collect canonical hypergraph vertex ordered. Or collect correct canonical vertex ordered hypergraph, but it's the naming is I made it like this. Yeah, so it just multi extension of symmetrization of this composition. And what is the vertex ordered insertion? The vertex ordered insertion is kind of the heart of this construction, doing precisely what I said. So inserting the hypergraphs into each other. But what is actually the know-how about this are the signs in order to get the relation. So one sign is here, and another sign is in this insert vertex ordered hypergraph inner. This is actually the very heart of the construction, which is merging together the vertices. And there is another sign which looks like this. And in order to obtain this, you really have to kind of go into the relations and try to figure out the correct sign so that the relations hold. It turns out that this sign is actually also can be viewed as a causal sign. If you view vertices as having degree 1, and you imagine that you take the vertices of the second hypergraph, you put them in line after the vertices of the first hypergraph, and you take the vertex where you are going to be inserting, you take it to the front. You're already getting causal sign by skipping the other vertices, and then you take the second hypergraph from the back, and you insert it, skipping over all these rest vertices of the first hypergraph, obtaining sign, and you insert it in place of the first hypergraph. So this is the sign is more or less natural, but in order to get it, you need to compute a bit. Good. So this is the definition of the bracket. Now I can show you how it computes. So let me consider some example hypergraphs. I don't need to mark the root here because we are considering this vertex ordered. And now I want to compute vertex order insertion bracket of the hypergraphs 1 and 2. Yeah, so of these two, and I'm gonna get some association, some vector of hypergraphs, which looks like this. See, there are coefficients also -1, so not only ones. In the same way, it's multi-bracket, so I actually can compute the vertex ordered insertion bracket of 3 elements: 1, 3, and 5. 1, 3, and 5. So these guys. And if I again apply it, label vertices. Now it's computing. Still computing. Also, it should. I don't think that it's so slow. My computer is very slow also. And see, and you are getting another result, another vector of hypergraphs, of vertex ordered hypergraphs, which is pretty long in this case. You see that there is something happening because there is somewhere is 2, for instance, here is -2, so there was some this summing up the isomorphic graphs actually did something here, and this is how the result looks like. And in the same way, you can basically, and you see that it's basically insertion, that it's inserting, that it's like a chain of insertions. Here, it probably comes from inserting the 5 to the 3 to the 1. Yeah.
So, Pavel, just one question, also to I guess ground some of us who might be, missing out on the complexities of all the construction. So these are hypergraphs where the sequential order of vertices,
Yes.
right, is always kept, right?
Yes. Yes.
So you are counting over isomorphism classes of hypergraphs, but
Yes.
you are basically fixing the underlying sequence of vertices, right?
Precisely. In
Okay.
this case of this graded bracket, yes.
Okay. I understand.
I will also have a remark about this maybe.
Okay. Yeah.
Short more.
Go on, because if that's clear, yeah, I can follow.
So this is really like isomorphism classes as vertex ordered hypergraphs. So you fix the sequential order, as you said, and you really, in order to check isomorphism, you just have to basically go through the vertices and map the vertices by the identity, basically by just the renaming, and check if the hyper edges are the same. So this is actually very easy, and yes, so basically here you can also compute another example is here. But it's interesting actually that already on this structure there is some graded structure. It is a graded bracket. It would not exist if I did not consider the grading. But already kind of on these guys there is some structure. And this code I already explained you. Okay, good. So I can move on. So this is the graded vertex ordered bracket. Now I will show you, and this is actually the new thing.
And this is sorry, and this is what kind of, so you say it's a well-defined multilinear operation, NRE multilinear operation on vertex ordered isoclasses of hypergraphs.
Yes.
Or I should say isoclasses of vertex ordered hypergraphs, right?
Yes.
Okay, so what kind of bracket is it?
Yes, so it's I don't know what it is for n, but I know what it is for n equals 2, and for n equals 2 it's a graded Lie bracket.
Okay.
Yes, so it's a graded Lie bracket for n equals 2, graded Lie bracket for n equals 2.
Yeah.
And basically, if you don't know the relations for Lie bracket, you can decode them from this Mathematica code. So L is in this case the bracket, and X is the sequence of inputs. So you are basically applying the bracket to X, and to the bracket applied to X2, and so on, blah blah blah. And this sum of these terms, and there are 3 terms. There is this term, then there is this term, and then there is this term, which in the graded case is actually acquiring this sign, additional sign. And the sum of these elements have to be 0. This function is kind of testing the Jacobi identity. It will take the bracket as a parameter and the arguments as parameter, and it will evaluate it on it, and it will give you the sum of these terms. And if it is 0, then the Jacobi identity holds. If it is not 0, it does not hold. In the same way, but it's sort of trivial, you can also test the graded symmetry. Graded symmetry is basically if you flip the 2 arguments, then you obtain the same thing up to sign. Yeah, and graded Lie bracket is a bracket. It's a graded bracket which preserves the grading and which satisfies this graded Jacobi identity and the graded anti-symmetry. Good. So just to prove you that it's actually satisfies. So for instance, on the previously defined examples, you can test symmetry. It gives 0 association. You can test. Now this is fun. This is test Jacobi identity. When I was running it for the first time, I was like, wow. I hope this is gonna work. Yeah, but sorry, but actually it is really giving 0. You can even change the
so here's
parameters.
Yeah, so here's basically the idea is that you've chosen sort of generic enough hypergraphs that you can just throw like some random stuff, small stuff, so compute time is lower, and you do get like true, right?
Yes.
It's not formally verifying.
No,
That
not
this
at
true
all.
in general is just checking it, right?
This is just checking it, testing it. This is no formal proof. I have just only proof which I have is like mathematical proof.
Yes. Of course. Okay, fascinating. That's wonderful.
Yeah, and so this is basically, and I would say this is like the native structure, which is graded, and it's like on the most kind of most concrete things, which are really this just the vertex ordered
Right.
hypergraphs, which now
Right.
makes it native.
So
Good.
it to me, I mean, people are gonna just think again. Carlos is coming up with the hierarchy stuff as usual, but I mean, this construction seems completely agnostic to the arity, right? Like it seems that you constructed an NRE operation for vertex order hypergraphs, right?
Yes.
It's completely agnostic. So
Yes.
I'm just burning curious to see if the ternary case would satisfy the ternary Jacobi identity.
Yes, but I decided to do everything step by step, and now I'm
Yeah. But how expensive is that computation for the ordinary Jacobi for the small hypergraphs that you had?
not expensive at all. I can just implement the how is it called, this how are these relations called, Lie n or N Lie relations?
N-Lie, yeah. The N-Lie.
And I can be checking for both of them. I just have to write them like this, and then I can start checking. But I mean, this is but this is the graded case. This is the graded case. I don't know how to take graded N-Lie, for example. If there is even such a notion like graded N-Lie, probably yes. But I will actually let me actually.
Yeah. No. I was just gonna say that when you check Jacobi, I mean, we can come back to this. Just go to the end of your presentation, and we can come back to this. Yeah.
Absolutely. So now I just wanted to explain you why the Jacobi identity holds. So just from the mathematical viewpoint, so basically you can view your bracket as a commutator of this insertion operator, which is here denoted by T. It's a graded commutator. So there is this. There are the gradings, and then if you rewrite the Jacobi identity, the Jacobi term, you can rewrite it. This is just a simple algebraic computation. You will see that it can be written as the sum over all permutations of the elements of these. The plus minus is always the causal sign, and of the differences of this associator, right? And in the case of these insertion brackets, basically this sum vanishes, not because the vertex or the insertion operator is associative. It is not, and I will demonstrate that it is not. But it vanishes because this I should have written it like here with this to keep the convention. It is vanishing because the associator is symmetric or graded symmetric under the exchange of G2 and G3. Yeah.
Interesting.
And here in this sum you are summing here should actually be also minus one to the sign of the permutation.
Yeah.
Just write sigma. So you are summing over the anti-symmetric causal sign. So this plus minus is causal sign, and this is the sign of the permutation. And basically, if this term is graded symmetric, then you're
gonna pick up a plus and a minus, and they're gonna cancel.
Yeah, precisely. Yeah. So this is it. And basically, this fact that this associator is symmetric is a consequence of the fact of actually there should be some nice visualization of all this, which I still did not kind of implement or find out. Basically, this symmetry here is a consequence of the fact that for the insertion, the following schematic relation holds, namely that if you are inserting G3 into the insertion of G2 into G1, it can happen only in two ways. Either you insert it basically to you insert it to the part which belongs to G2, and in that case it is the same as if you inserted it to G2 first and then you inserted the result in G1.
Yeah.
Or you insert it to the part which corresponds to G1, and in that case it is the same as if you were inserting G2 at G3 to G1 at the same time at different vertices.
Yeah.
And this thing is graded symmetric.
Mm-hmm. Mm-hmm.
And this thing cancels with this thing. So that's
Mm-hmm.
the reason why these relations hold. And now I will illustrate you that they are not holding because this T is associative.
Yeah.
Here I just compute the associator of this.
Yeah.
Why did it compute here? It's somehow too much. Wait, I have somehow. Yeah. What is this? What is this? I need to delete this. And I don't need the roots. I can just have this. Yes. So basically, the associator is not zero. So it's not vanishing because of the associator zero.
Yeah, it's very. It's quite. I think it is quite intuitive that this operation should not be associative, right? Because, I mean, you're doing some kind of averaging of insertions, right? Like it shouldn't be associative, right?
Yeah.
Like if you're doing a single insertion, then maybe, but because you're doing this all possibilities summed over, it really kind of abstracts it from being associative, which is what makes this so interesting. Yeah, very cool.
So now I want to say, actually, in contrast, the Jacobi term for the commutator bracket, you can basically, if you have two linear operators, you can do endomorphisms of some vector space, you can consider a commutator or the graded commutator.
Yeah.
And this commutator also defines the Lie bracket, but the Lie bracket is trivial, vanishes trivially because each term in the sum vanishes because this T is associative.
Yeah. Yep.
And now, actually, what is also my kind of finding? Actually, this is what I find kind of cool, and but what still needs to be tested and written actually properly down. And this claim is actually in the non-graded case, which will come on the next slide. And namely, if you actually map a rooted hypergraph, so it's a hypergraph with a specified root, with one vertex specified. If you map it to the rewriting rule, which basically looks like just on the left-hand side you are having the root, and on the right-hand side you are having the hypergraph. So it's kind of embedding rule of just one vertex to the hypergraph.
Wait. I want to understand what that rewrite rule looks like. So
yeah. So if you are having,
what does the rule do?
yes. So if you are having, for instance, you are basically gonna. It's also on the next slides actually. But if I have, for instance, this hypergraph 1 to 3, then the corresponding rule, and if the root is 1, yeah, with root 1, then basically the corresponding hypergraph rule is just the hypergraph on the vertex 1, just with no hyper edges, and this previous hypergraph. So let me hack it somehow. AHG, and yes, and now, so for this hypergraph with root 1, the corresponding rule where you are mapping looks like this. On the left hand side is only the root. Yeah.
Oh.
So
it basically inserts, right?
Yes.
Okay.
So this claim, I don't know if there is a graded version of this claim. I don't have it yet. For this, you would have to define some kind of graded application of rules, which I don't know how.
Okay.
But in the non-graded case, if you map the rooted hypergraph to such a rule, then this rule, this rewriting rule, can be actually considered as a map, as a linear map on isomorphism classes, on the vector space generated by isomorphism classes of rooted hypergraphs. How? Because you just, if you apply it to one single rooted hypergraph, you just apply it in all possible ways and take the sum. So take the vector which you obtain like this. So it's a linear and it extends in a linear way.
Yeah.
So you are basically mapping isomorphism classes of a rooted hypergraph to a linear map on the isomorphism classes of, on the vector space of isomorphism classes of rooted hypergraphs. And actually it turns out that this map is mapping the insertion bracket is mapping to the commutator of the rules. Yeah, which is a funny fact, because here basically you have the Jacobi identity for the insertion bracket based on this phenomenon. Then you have the trivial Jacobi identity for the associator, and this map, I'm just claiming that this, if you view these rooted hypergraphs, if you actually view them as rewriting rules of a special form, and you view these rewriting rules of special form as linear maps, then the bracket gets mapped to the commutator. This I find kind of interesting.
That's super cool. Yeah, that is a really interesting fact.
Yeah, and this I'm kind of quite already kind of quite sure, I would say, but I did not write it down like properly yet. So, but I would actually, I would say I already noticed it in the Wolfram Winter School. I would say that this is going to hold. And just a question for discussion. So why is here Lie algebra? Why are we getting such Lie algebra? Where does it integrate to? Just to note, these are infinite dimensional Lie algebras. So they are not, there is always like infinite dimension here. And if you can somehow reintegrate it to some Lie group or whatever, what is it? What does it correspond to? Yeah.
Are they? But they are over integers, right?
They are over integers, yes.
Yeah. I don't. Unfortunately, I was talking about this with my ex-supervisor last week, actually. I mean about integer Lie algebras and things like that. But I don't have right now within Grasp because if they are integer in some sense, they are not even in the class of like Lie algebras proper, like that we understand geometrically.
No, I mean every integer Lie algebra you can obtain like real Lie algebra. You can just plug in real coefficients. This is not a problem here. This is not a problem. You can also evaluate it. Have a look. You can also. Where did I have it?
Yeah. So, but do you know? Okay, I see. But then all integer Lie algebras become, well, not necessarily, but these have an infinite basis because
yes,
because we have infinitely many iso classes of hypergraphs, right?
Precisely. Yes, they have infinite basis.
I understand. That's interesting. Okay, yeah.
The question is, of course, is there some finite dimensional subalgebra? I would say no, because actually you are always inserting something, so you are basically stacking up things together, so it always grows. So I cannot imagine that anything closes under like any finite dimensional subspace closes, because it cannot. It just grows each time. It grows all the time. So there are no finite dimensional subalgebras, I would say.
As a side comment here, I don't know how to go forward with this comment, but it would be interesting to kind of counterbalance. I mean, this is fascinating. You're relating a rewriting rule to a linear map. I mean, let alone the homomorphism condition that you suspect, but just connecting a rewrite rule to a linear map, it's already a lot of progress, because it's sort of bridging two worlds that don't really talk to each other that well. And And I think that if you have a rewrite rule interpreted as a linear map, there is the very, natural extension of this idea, which is to say, well, this rewrite rule really is just insertion, right? Seen as a rewrite rule. So how about you can, and insertion is always additive, right? Like your edge count always grows, your vertex count always grows, So the question is, what if you deal with some subtractive rewrite rules, right?
Yes.
And then you can have you can start to really hypothesize that there are finite dimensional Lie algebras, that they're like really interesting animals walking around, not just like Lovecraftian gods in the infinite,
The question is, I mean, in the infinite dimension also have some interesting, for instance, would be fun to find some kind of a Virasoro algebra or something like this, right? Or this string theory algebras or something like, maybe they are represented by some subsets of hypergraphs in this.
Yeah,
in this thing.
Definitely. Yeah. I mean,
but actually, I'm afraid that this relation, if you subtract something, then this principle that basically gluing something into the gluing is gonna be like this. It's gonna split into these two parts. If you think about subtracting something, so you are basically subtracting G3 from G2 subtracted from G1. You are not gonna get this. So the question is, if subtraction rules are gonna be even have chance to define any Lie algebra. This is definitely super cool question. If there are other kinds of rules which define Lie algebras, and the only what I know about are not only these vertex rules, but for this I have to switch actually to another slide. Where I define these are the tucked edges. There are also the hypergraphs with the tucked edges, which are also giving Lie brackets. So you are basically having here tucked edge. But this is not the topic of today's talk.
Yes. So, sorry. Yes. Just maybe get to the end and then we can expand on. I have a couple of questions that I want to explore.
I just wanted to here make a note on computational complexity. So for the vertex ordered insertion multi-bracket, it's quadratic in number of vertices and factorial in number of arguments, which is not that bad. I mean, factorial in number of arguments, there is always this anti-symmetrization, but quadratic in number of vertices, it is this based on, there is the crucial fact is that checking for isomorphism is linear in number of vertices. This is what we just discussed with Carlos, that it just really like sorted stuff, which is actually contrasting to the rooted insertion multi-bracket when you consider this insertion, this up to isomorphism of rooted hypergraphs, where you actually have to check for like real hypergraph isomorphism preserving one vertex, and this is still exponential complexity in number of vertices. So as soon as you introduce more complicated isomorphisms, you get higher complexity, of course.
Right.
Yeah. And now let me show you also now this was the graded case, and let me show you the insertion Lie bracket on isomorph classes of rooted hypergraphs. So this is the non-graded case, and it's constructed in the same way as the insertion Lie bracket on vertex ordered. Only I still have the vertex ordered insertion, but now I basically take the absolute value of all the coefficients. I don't care about the sign. I just want to make it 1 everywhere. And now I also replace this collect canonical hypergraph vertex ordered. I replace by collect canonical hypergraph rooted. Yeah, and collect canonical hypergraph rooted is just basically transforming rooted hypergraph to its canonical version as a rooted hypergraph. Now this point is a bit subtle, needs a bit thinking, but how do I construct a canonical? What do I claim is a canonical form of a rooted hypergraph? So the property of the canonical form which I want is that two rooted hypergraphs are isomorphic as rooted hypergraphs if and only if their canonical forms as rooted hypergraphs are equal. And I'm claiming that you can get such a canonical form by you first convert the root to a tucked unary edge. Yeah. So you are adding a unary edge with a tuck. Then you are applying the Wolfram Institute hypergraph function canonical hypergraph, which is preserving the tucked unary edge. And then you are removing the unary edge and converting it to the root. And these basically the root is, by converting a vertex to a root, means just that you put it on the first position, because somehow I consider vertex which is in the first position in the vertex list as a root. So you just move it to the first position. And I claim this is a valid canonical form because vertices of a canonical hypergraphs are always 1, 2, 3, and so on. So if you apply canonical hypergraph, then the vertices are always range. So if you have here some root at position I, then you obtain the canonical rooted form is going to be like I, 1, 2, 3, 3, and so on. Yeah. So this is one kind of technical point which one has to think through to be 100% sure. And yeah, so this is just, but the construction, you see, it's the same thing. The way kind of how I implemented it, it's can be written nicely like this.
Mm-hmm.
And now to give you some examples, again, you can compute, oh yeah, what happened now? Wait a second. Now something happened. I hate it. What is HG actually? HG is okay. We redefined HG somewhere. I have to get back to the initialization cell. I can just say somewhere here recompute initialization cells. Wait a second. End presentation, and I will go to the definition of HG. Where is it? Where is the definition of HG? Created LibreCAD. No examples here. I will just re-evaluate it, and then I will move back to this here, and it should now evaluate. Yes. So now it is evaluating. Oh yeah, it's been. Now I am again here. Yes. Rooted LibreCAD. And rooted multi-bracket again with this is the interesting, this is the LibreCAD, the multi-bracket interesting for Carlos, because this is actually makes sense to really check if it is like Lee algebra or Lee tree algebra. Yes. So again, you have the same thing. Again, you can test symmetry. Again, nothing. You can test Jacobi identity. You can test Jacobi identity with permuted inputs.
Really cool.
It holds by the tests. Yes, and now I also wanted to actually, but this I did not manage to prepare because I was short on time. I wanted to also test basically this claim here, but this I did not manage to bring to the end.
No worries.
Where is the test? Yeah, the map side.
Yes,
yeah.
yes.
So
well,
maybe if you want to discuss this, to get kind of to close this topic, and then there are additional ideas in the Wolfram, in the summer school talk, in the winter school sheet, and like for instance how to get Poisson algebra from that, or with this is actually my next goal. My next goal is to implement this tucked bracket in the same nice way as I now implemented this with the root vertex. And yes, there is actually there are actually multiple ideas which one can kind of explore more. Yeah.
Well,
but this is the first step. Yeah.
Yeah. No. Amazing, Pavel. Well, thanks very much. So before we get into more specifics, I wanted to, so in summary, right, just as an overview for those of us who are not experts and who want to, have a summary of what was just presented, you basically identified some particular classes of hypergraph-based objects, like rooted hypergraphs, where it's basically a hypergraph with a singled out vertex, and vertex ordered hypergraphs, right, where it's basically that, but extending the singling out to every single vertex in a ordered way, right? And what you did was you constructed isoclasses of those objects, considered formal linear combinations of those isoclasses, and then via implementing operations on the objects themselves, on the representatives, the actual elements, with very graph native constructions, i.e. insertion, right, where you put one graph into another just by merging at one vertex, you were able to obtain Lie brackets, right? In one case, just classical Lie bracket, and the other graded Lie bracket.
Yeah.
So one of the takeaways for me, before getting into more specifics, one of the takeaways has been the fact that, hypergraphs themselves, or isoclasses of hypergraphs period, seem to be insufficiently structured to sustain something like a Lie algebra. So I'm interested in your intuition on the necessity for this peculiarities of like rootedness. You now talked about a tagged edge, having vertex ordering, and so on. I mean, I can reformulate my question by asking, is it possible to define Lie algebras on isoclasses of hypergraphs? Just no extra singling out of vertices?
I would think actually there has to be something what in a way something because it's there has to be some anti-symmetry introduced, and I honestly don't know how to introduce this anti-symmetry if you have just isomorphism classes. I would think I would not expect that there is a Lie bracket purely between isomorphism classes of hypergraphs. I would expect that there is a Lie bracket on one hypergraph on the vector fields, as Dugan is doing and so on, but not like in this way. In this way, I would not expect.
Sure. Yeah. No. It was more of a rhetorical question to follow up with, saying that as you say, that I think it's a very interesting intuition enabling fact, right? Like when you. I mean, many of us who have worked with Lie algebras as the primitive object, right? I mean, normally I would start with let a Lie algebra be this or that, or let a Lie algebra be this or that, and then you start to sort of make inquiries. Instead, this seems to give you an insight into why these objects are as important as they seem to be, right? Like this seems to be a case where you have a space of options, possible hypergraphs, and you have to somehow define a sequential element to it, or at least create some form of asymmetry, some kind of configuration asymmetry or something like that, right?
Absolutely.
And I think it's interesting that when you look at mechanics, you first find Lie brackets in the context of motion, right? It is. I mean, one parameter subgroups and these kinds of things, they are the mathematical representation of motion. So maybe that's exactly the asymmetry that one is looking at, right? Like when you have one particle moving space and another particle moving space, the objects that one would represent are vector fields, which are nothing but their trajectories sort of integrated, right, or infinitesimally. So I don't know, I'm just trying to draw some kind of parallel to make sense of the fact that you have to sequentialize vertices on the one case, which is kind of like having some kind of path with shape, right? Like you have a path that is the sequence of vertices, and it has like a shape, which is, you know, what edges exist on those. And then you have two of these things, and maybe classes of these things or whatever, but effectively you have two paths with two shapes, and you are kind of doing this commutator, you know, usual kind of flow of thing. You know, I don't know. I find it interesting. Oh, we can see you now. Very nice.
But now the background is not blurred. I need to,
yeah. So the fog of graded Lie brackets just disappeared. It's like very symbolic. But yeah, anyway, so I was just making it, just thinking out loud that trying to connect the Lie bracket, because, you know, in some sense, when you look at a Lie group, right? If one takes the usual geometric perspective, the differential geometric perspective on Lie brackets, you have a Lie group that doesn't have any anti-commutation in it, right? Like it doesn't have any anti-symmetry built in, right? It's just the space, and it has an associative operation, and, you know, it is what it is. However, when you look into the infinitesimal component, of course, you have a built-in anti-symmetry because you have the notion of negative, you have the notion of inversion, and so you do have some degree of introducing that sort of set to alternation, but.
And you also have the notion of kind of moving infinitesimally by one path and moving infinitesimally by another, and then doing it the opposite way. Yeah.
Yes, exactly. Yeah. So anyway, that's very interesting. I really think that this. I mean, I feel like I've learned, like just listening to you today and in our previous conversations. I feel like I've learned not just the actual technical contents that you presented, but I feel like I have developed a little bit my my Lie bracket lore, like in my head, you know, like I've pushed forward a bit how I understand Lie brackets, and I mean this has been, I have to say, a bit of a discovery. Also, shout out to Manu Manduri, who was involved with the Institute for a while. She was doing this project, and she's now moved on to do a PhD. So all the best to her in her new life. But you know, she was the one that explained to me this insertion algebra in the Blackboard in Paris a few months ago for the first time, and you know, it was, to me, it was kind of eye-opening to say, okay, right. So I've been so focused on continuous structures, continuous geometry, differential geometry stuff, but clearly these systems that are small combinatorial, you know, like graphs or hypergraphs and so on, they also seem to speak Lie, you know, like they seem to speak Lie geometry, Lie algebra natively, right? And so that's, I think, quite insightful.
There is actually, I come from the field of string topology and symplectic geometry and so on. There is a lot of also Lie structures, which are basically, for instance, in string topology, they are also based on like connecting or disconnecting loops in a way, or having like, yeah. So it's, I honestly, I don't see where these hypergraph constructions, where they lie. If one could maybe one could represent some string topology Lie bracket in a way by some hypergraphs or something. Maybe one could find that it's the same construction which happens in topology somewhere, just done in this way. It's kind of, it's definitely interesting. Where does it come from, and also what is the Lie group? Because basically you consider vector spaces because you want to study diffeomorphisms in a way, and yeah, you consider vector fields because you want to study diffeomorphisms and their group, and here you actually go the opposite way. You have the Lie algebra, and you don't know what is the Lie group in a way.
Yeah, no, for sure, and yeah, and it's very interesting as well that the formal the formal linear combinations of hypergraphs, I have to recognize, you know, the power that the construction has, but at the same time, I was always kind of suspicious and a bit skeptical, because I thought, oh, this is just kind of throwing everything into a bag, you know. It felt a little bit artificial, but really, when you think about the notion of a formal linear combination, that's basically just a multiset, right? It's essentially it may be a signed multiset, but I think that's very fair as a data structure. You're not cooking up something completely esoteric so that your mathematical dreams are attained. It's more like, hey, I have objects, and I want to think of like the defect of an object and the presence of an object, so I give it signs, and I just assign multiset, right? Like if I have several copies of the same thing, I'm going to keep track of the total balance of copies of this object. But I don't know. I mean, really, that's what formal linear combination is, right? And the fact that you have this linear algebraic structures living there, I find it very, very interesting. So actually, before continuing on a more conceptual level, I was curious. So you said that it would make direct sense to check ternary Jacobi on the rooted one, right?
It would make sense. It would make sense, definitely. It's the tempting, right?
Yeah, I mean, should we do it live? I mean, the formula is so simple.
Okay, we can try to do it live, but it's going to be a huge disappointment if it's not going to hold.
Yeah.
Right.
But well, I mean, we will learn.
But this is not. I just want to tell you. So this is just you are gluing them in chain to each other. So if this does not hold, you can still consider like gluing them to some common join. You can imagine that you are not just chaining them. You can pick like a simplex and you can glue them. You can play with it. You can try to search actually the structure.
Yeah.
But we can actually check out this thing live. Yeah, I have to wait. I have to share my screen.
Yeah, I will send you the formula if you want, because I have it just with me.
Or maybe you can just dictate it.
It's just quicker if I send it, because I'm just gonna just give me 30 seconds. I mean, it's exactly what you expect, but maybe I can dictate so it's more pedagogical.
So wait. So I will copy this to the end. I will put here insert new slide, and we are checking how is it called? It's the Filipov.
Yeah, Filipov. Yeah, people call it a fundamental identity or Filipov identity. FI. I don't like fundamental identity because it masks the fact that it's Jacobi for n equals 2. But yeah.
Good.
So yeah, double P on Filipov, but
okay. And we
yeah,
are not having any degree, right, this time?
No. So this is this is just. Yeah. So that would be L, and X is a list of 5, right? So basically you write that same thing, right? So it's
so I think it's like the derivation, right? So you are having
it is exactly a derivation. It's exactly a derivation.
So you are basically
it's a self-derivation.
So you are basically deriving here in the last component. You are plugging in the, so it's going to be here x2. Then you are.
Wait. So you have to be plugging. Wait. You need to be plugging. You have one too many L's.
How about this? Sorry. Okay. This is not here. This L is not here.
Yeah, x2 is just x2. That's right. That's the first term. That's correct. Yes.
And the second term is gonna be minus. And now it's gonna be the derivation goes in, and it's basically deriving the first term. So it's gonna be
correct.
L x 1 x2
correct
x2
on 3
x3 yes.
Yeah.
Now x4
and now x4 x5
x5
and just the same, the other two terms.
And now it's going to be minus L, and now we are having x3 in front.
Yeah, we're keeping the
and now still L. Maybe I should have copied this derivation. Actually, this may be.
Yeah, derivation is easy to copy. Yeah.
Copy this.
Just.
Now I'm applying it to x4. I'm evaluating at x5. And still minus, right? It's
Still
just
minus,
on
yeah.
the right side. Okay.
This is the same.
X3,
X3, X4, and then the same.
X4, and the derivation of X5.
Yep.
Bam. Now we are computing this.
Yeah, just
I can delete this thing.
Mm-hmm.
Why is this here? Error here is missing. Just let me check it quickly. So we are having no degree. Degree I can delete completely. It's just this function. Just this function. Just this function. Good. So I can now, and we can test it. So we have these graphs AG. So I can put there. We have actually precisely five graphs, right?
Yeah.
What's the length of? It's 5. So we can actually.
They have to be rooted, right? Or they are by the first.
Yeah. They are canonically rooted by the first vertex.
Okay, sure.
Yeah, this is how it is represented here. And now I can do test Filipov, and I can do the, how is this called? Rooted insertion bracket. Rooted insertion bracket, and I can apply it to the list of hypergraphs, to HG. And now it should do something. So just a disclaimer. So there might still be some, it needs also the definition of the rooted insertion bracket might still need also checks. So everything. So if this does not hold, it does not mean it does not hold. It still might hold if one removes all implementation errors, but maybe it holds. Who knows? It's computing now.
This is.
But it might actually. It might compute very long time because basically you are having 5 elements. You are doing 5 factorial.
Yeah.
I'm not sure if I will
make
it on my i3 processor from 10 years ago.
Yeah. So while this computes, just for intuition, so the triple bracket, as you said, is doing it in a chain. So so in a way, is it a composition of? I know there's a linear combination, linear extension that it's involved, but at some point there is the first argument inserts second argument and then inserts third argument, right?
Yes, you are asking if this thing which I'm doing basically as one operation, if this can be written as composition of the binary operations, as a chain of the binary gluings, like of the linear operations of binary gluings. I don't know. Probably, I don't know. Maybe yes. Maybe I would
wait.
say
So what I'm asking is, what is, like, how would you explain what the bracket of H1, H2, H3 would do? Like just that bracket.
So you take these 3 graphs and you take the last one. You are gluing it in all possible way to the second one, and this gluing you are gluing in all possible way in the first one. And then in the bracket, you subtract from this. Wait, in the bracket you are summing over all possible permutations of these 3 elements. So yeah, I want to say I don't see now what it could be, but maybe actually a way how to understand mathematically is by writing it as just a composition, maybe like folded binary vertex insertion. Maybe who knows? Let's But I don't have intuition now. If you see something, then it's great.
But yeah, because one of the funny things is that if you have a Lie bracket, you can always do the double Lie bracket, and that thing is a 3 Leibniz up to the antisymmetry in 2 arguments. you have, yeah.
So wait, so if you define a bracket like how? Like
Yeah,
this?
like A, B, and then C. Yeah, just like that. That's a ternary so-called Leibniz bracket. So except for antisymmetry in AB, sorry, in BC, that's a Leibniz bracket. That satisfies the Jacobi identity. That satisfies the formula that you have above, the Filipov thing.
Okay.
So
it satisfies Filipov, but not anti-symmetry.
yeah, because I mean you can see just from the formula that when you permute, you know, A, B in block or A and B individually, it anticommutes, but if you permute B and C or A and C, it's not gonna, in general, it's not gonna anticommute. So if you antisymmetrize it, then you do get a Lie bracket.
Okay, so if you take anti-symmetrization of this,
yeah,
so
that is antisymmetrization of that. It's always a ternary Lie algebra. It's always a 3 Lie algebra.
Antisymmetrization gives always a 3 Lie algebra, which is the Filipov algebra above, right?
Yeah.
The
It satisfies that property.
Yeah.
And antisymmetry. So that's what people call Filipov algebras.
Really
So in a way, those are the like the boring ones because they are completely determined by Lie algebras.
If I should guess, then I would think that if this is this thing, then it's going to be the boring one.
The one above.
Yes, I would think that if this satisfies the Filipov identity, if my bracket satisfies this Filipov identity, then it's going to be the actually this anti-symmetrization of Leibniz bracket. I would just guess because it seems that there are some kind of relations.
Well, but that's why I was asking, because it would be, I think it could be quite transparent to just understand that fact at the level of brackets, because the only thing you need to check is that formula, the definition that you have there, you know, like bracket ABC equal bracket AB and then bracket C, right? I mean, that's a formula that you can just check if it's true in your up to some antisymmetrization. I mean, you might need some antisymmetrization, right? But
Okay.
it's a much simpler formula to check
stop
than.
this computation. I stop now the computation
Yeah,
because
yeah,
I
yeah.
think that we would never
Might be too long. Yeah, might be too long.
And I can check this computation. Cool. So now we are actually doing research like directly with
exactly
the notebook.
This is what this is all about. We are
Leibniz. Test Leibniz, and you just take to LX3, and now you just take the double here.
Yeah, and rooted. It's gonna know what to do, right? Because it's gonna know when it's taking 2 arguments or 3 arguments, right?
Yes.
Okay.
And now I do test Leibniz, and I put this rooted, and I put, well, yes. So so it gave actually some non-trivial result, which means that the test does not hold.
Yeah.
So it does not seem.
It shouldn't hold, because the left hand side is antisymmetric and the right hand side isn't.
Yeah. Yes. Sorry. You are right. Sorry.
So it should not hold. But the question is, maybe it's easy to understand that. Yeah, if you antisymmetrize.
Oh God. Okay.
This antisymmetrization is a little bit tricky, I think. Wait, so you
maybe I can.
antisymmetrize on, I believe if you antisymmetrize on second and third, you should be fine. Because
Second and third.
yeah, or first and third. Because you have antisymmetry on first and second, and antisymmetry between well, is that antisymmetry? It's not even antisymmetry. It's some kind of weird.
It's not like. I think this is also not going to hold because this is not anti-symmetric here.
No, no. Maybe you have to just do full antisymmetrization. So you antisymmetrize for 1, 3, and 2, 3. Yeah, actually, yeah. No, I was wrong. Because using the antisymmetry of the outer bracket doesn't do anything because it changes the base definition of the ternary bracket. So yeah, it's just full antisymmetrization. But I mean, this is so cool that you have code where this can be tested. This is just amazing. Let me just point out. Wait,
no.
It should be. Should be only 4 terms, right?
6 antisymmetrization, or?
Well,
like
I mean, it's already antisymmetric in 2.
Ah, okay. So yeah. So you're right. So I'm just.
I mean, it shouldn't make a difference, right? it really shouldn't make a difference, but you write less.
Wait. So yeah. I never thought about kind of partial antisymmetrization of this stuff. So you are saying I don't have to antisymmetrize.
1 and 2, you don't have to antisymmetrize.
So there is just this bracket, and now
So
I have
1 and 3, that's the 2 and 3 antisymmetrization, and the 1 in the bottom.
Yeah, but I have to antisymmetrize the result of the previous antisymmetrization. So now I have to antisymmetrize this in. I always have to come.
Yeah, maybe just antisymmetrize the whole thing and we just call it a day because it's not that many.
Yeah. So I antisymmetrize the whole thing, but then actually, yeah. Okay. Let's see what it's going to do.
It should be fine. I mean,
yeah.
I mean, for Jacobi, it's not going to matter because we might pick up some integer coefficients, but like some constant coefficients.
Oh.
Yeah, but this is the real question. So let's see 1, 2, 3. So 1, 2, 3, 1, 3, 2. 2, 1, 3. Okay, so is that everything? 3, 2, 1, yeah. Okay. Make sense? Okay, so before you compute it, can you show the just print HG so we can see just for visual reference somewhere? Okay, just make him quite small so it fits in a line, so we can just keep that visually. Yeah, just make that smaller. Okay, cool. So we have those 3. So can you compute one pair and then the triple, just to see visually the result.
Of one pair?
Yeah, just one pair or whatever, like 1 and 2. Just do 1 and 2 and then 1, 2, 3.
Of rooted insertion bracket, I mean like
Yeah,
this?
yeah, the one that we're gonna test for. So this is just for everyone's kind of visual aid. Right. And then do the rooted insertion bracket of 1, 2, 3. Yeah. So that takes a bit longer. Makes sense. Okay, so okay, let's understand this just again for everyone. So we know what we are testing for. Maybe start computing the symbolic thing. I mean the test.
Right, so now I have to.
Should be.
It's test Leibniz good. So here I have to compute here, right? Make
Yes.
that. Yeah. So.
Yeah. So while this is computing, just scroll up. Okay. So the first one, just insert it, right? It makes sense. It inserted in 2 ways, right? Basically. Okay. And then we have some weights going on, -1 and 2. And then the third one, so the second one, it's doing, can you scroll down a bit so we see? So that's just a chain of insertions. There's a chain of insertions. Yeah, they really are all chains of insertions, right? As you said.
Yes.
Yeah, that I just wanted to make it visually clear what you said in words, so that everyone can see that these are chains of insertions. Okay.
And it's still, even if this now does not give the it gave actually something, but it does not mean, in that point it does not mean much. It means basically that either there is some problem in the implementation or not, and this bracket is something different.
Well, it will be very strange that you checked for several Jacobis, and I mean for the binary case, and it did check out consistently, right?
Yeah.
I mean that would be very strange that there's an error in the implementation. I mean, one can question about the implementation beyond pairwise insertion, but
actually, I have in this implementation there are some things which might require more thoughts. Like if this for instance canonical form is valid, it uses kind of the assumption that canonical hypergraph is always has these vertices 1, 2, 3, and so on, which I hope is true because it's written in the Mathematica manual.
yeah.
And yeah, and also I also need to, of course, I need to. This is I was testing on different combinations of these vertices or just some example graphs. So I need to like prepare like full test set. Yeah. Full test set to be sure that the implementation is correct. I'm pretty sure that it holds as like theoretically, because it also holds for the graphs, and this is basically the same proof. But the implementations, I mean, requires a bit more testing.
Yeah.
But actually, this is like indicator. This is also can be indicated that we are anti-symmetrizing wrongly. I mean, we anti-symmetrize. We take to full anti-symmetrization. Maybe one is not taking full anti-symmetrization here. I don't know. And
yeah, I mean, it seems like, because it would be strange. Wait, did you say that can you go back to the mathematical definition of the bracket? Did you had some formulas, right, where you had the yeah
here.
So this was the graded case, right? But
in the non-graded case, you just remove the sign here, and your insertion operator is just disregarding any sign coming out of the construction.
Right. So the commutator is, so the bracket is the commutator of a non-associative binary operation, right?
Yes.
So this is what are called admissible Lie algebras, right?
What is what once more?
I think these are called admissible Lie algebras, I believe. Let me quickly check. Admissible Lie algebra. Oh, Lie admissible algebra. Sorry. Yeah. So I'm gonna share this in the chat for everyone's benefit. So basically, what I mean, it's one of the briefest Wikipedia articles I've ever seen. 2 lines. A Lie admissible algebra introduced by Adrian Albert in 1948 is a possibly non-associative algebra that becomes a Lie algebra under the bracket. Well, should say under the commutator bracket, but yeah, under the bracket, the commutator. Examples include associative algebras. Lie algebras, of course, because the commutator gives the same bracket, right? Okobu algebras? What is this? An Okobu algebra or pseudo-octonian algebra is an 8-dimensional non-associative algebra similar to the blah. Okobu algebras are composition algebras, flexible algebras, Lie admissible algebras, power associative. Interesting. Okay, so some fringe octonioid algebra is also Lie admissible. But yeah, but I mean, they should be noted here. You know, this Wikipedia should be extended because they don't mention insertion algebras as Lie admissible.
Because maybe insertion algebras are namely something already known, and namely left. How is it called? Left associative? No.
Oh yeah, that's right. That's right. Yeah. What was the term? Left. What to say? It's in the Marcoli paper, right?
Yes, probably yes. Yes. Wait,
Yeah.
I wonder if I have it somewhere. Or you find it.
Yeah. Just checking Marcoli here. There's reasonably recent stuff. So these are pre-Lie algebras.
Yeah, pre-Lie algebra.
Yeah, yeah.
Left and right pre-Lie structures. Yes.
Yes, pre-Lie. Yeah, pre-Lie. Yeah, exactly. So these are structures such that oh, right.
So just
pre-Lie
besides
algebras are Lie admissible algebras. Yeah. Yeah. Correct. 110 a group structure from a pre-Lie algebra structure. Interesting. Pre-Lie, I see, and pre-Lie basically. Yeah, so that's what you have here, right? It's pre-Lie because it's basically is what you say. This is symmetrical in the associator is symmetrical. It's symmetrical in the second, third arguments, right?
And basically, what we are doing is we are taking the pre-Lie operation and we are composing it 3 times in order to get the ternary bracket.
Oh, is that right? Ah, interesting.
I'm wondering if it is now.
Then okay. So wait.
If it is the same thing or not. I'm wondering if it is the same thing or not. Probably yes. It seems like that. It seems like that this insertion is basically, this is the question, if it's like the folded binary insertion or if it's something new. I would say it's folded binary insertion.
What do you mean by folded?
That basically the way how it is computed, that this how it is internally implemented, this vertex insertion operator is.
Wait, so okay.
So yeah, so there is, it also depends on the order of multilinearization, of linearization and symmetrization and so on.
Yeah. But so can you, so you said that you are composing the pre-Lie bracket 3 times.
Possibly,
But
although
so
not really clear.
Right, because if you were to do that, I mean, one possibility. So you don't know how you would write a formula for the ternary bracket right now. Is that true, or you do?
We have the ternary bracket.
Yeah. So what would be the formula in terms of
the
insertion?
But the formula would be, the ternary bracket would be x or a1,
Yeah.
and a2, a3.
Yeah.
And it's basically the sum over. Over all permutations.
Yeah.
Overall permutations sigma, and we are taking the sign of sigma as usual.
Sure. Yeah.
And right,
Okay.
and we are taking the like t a sigma 1.
Yeah.
Oh yeah, but just this ternary. I have actually, this is an anti-symmetrization of the ternary insertion operator.
But okay, so.
And now I have to explain what the ternary insertion
Exactly.
operator is.
Yeah. Okay.
Yep. Sigma 3.
Yep.
And now this t. This t is a sum. Is the sum over all gluings.
Yes.
Over all gluings of t of a1, a1, a2, a3 is the sum over all gluings. No, it's actually, it's just t a1, a2, a3 is, yes, also sum. It's a sum over all gluing over all vertices. And now a1, now there is this spread. What's symbol there? So let me write it like this: a1,
Sure.
a2, a3. So probably actually it is first gluing like this, and then gluing like this.
Wait. So okay. So but in the binary case, right? In the binary case, you had an actual commutator, didn't you?
In the binary case, I had an actual commutator. Yeah.
So my suspicion, and this is maybe just a suggestion here for not to check today, because this is, but my suspicion is, regardless of what this ternary one that you have on the screen is, my suspicion is that I would intuitively think of, if I have a binary operation, right, that applies twice, like basically that that wedge, right, like that pre-Lie. What I would say is set up the triple composition like it's written there, right, in whichever way.
Yeah.
And then anti-symmetrize that.
Yes.
Right.
This I do precisely that.
That's what it is?
No, but I mean, I'm computing this internally like this, like this, and then I'm taking for each input, I'm taking the anti-symmetrization, the
But why is that equal? My question is that equal to T of A1 and then T of A2 and A3?
Precisely. That's also my
Okay,
question.
okay.
So
T A1, 2, 3 equals.
I'm not sure. I'm not sure by this.
Okay.
Maybe.
But so even if it isn't, what I'm trying to say, right, is define a ternary operation to be T of A1 of T of A2, A3. Right? Just define it to be that. And then fully antisymmetrize that operation like above. Yeah, maybe call it something else. I don't know, but because if you have a definition for TABC, like I don't know, like S or whatever, yeah, and then that thing, I would suggest that you check for full antisymmetrization with the 6 terms plus and minus and usual thing, so that it becomes and then maybe that's a ternary Lie algebra, right?
And that in that case it would be more this trivial antisymmetrization of Leibniz.
I don't know. Would it? Maybe.
It kind of seems like that it does not contain any other information than this double composition, right?
Well, sure, yeah.
So I would not expect it to be.
But you think the scrambling of the antisymmetrization, it shouldn't do anything, right? Because
I have also this vertex ordered insertion operator.
I guess you should. I mean, it's not trivial that becomes the. Or is it trivial that equals the double Lie algebra? I mean, that's just an algebra problem, right? It's nothing to do with graphs. If you have two pre-Lie, I mean, if you have a pre-Lie product, I mean, we are agreeing that T is a pre-Lie structure, right? Okay. So if you have T that defines a bracket AB as the commutator of T, the question is, if you do the antisymmetrization of the double bracket, right? Basically what you wrote there. So if you do the antisymmetrization of S according to that, which is a triple bracket, and you fully antisymmetrize, the question is whether it's whether that equals the Lie bracket, the double Lie bracket, right? ABC equal question mark to bracket AB and C. I mean, this feels like just an algebra question, right? I mean, it feels like you have a, I don't know.
Yeah, for this I would need to take a piece of paper actually and somehow, but actually if using this is
what I'm trying to do here.
using this software, I could theoretically also try to cook up something from that because it actually computes anti-symmetrization. It has this symmetrization function, right? So
I can
somehow symmetrize it.
No, but I think it's fair. I mean, I was just asking for. I mean, we can continue conversations in the next few days for sure. But yeah, any questions from anyone else? Because I mean, I think we covered our slot here, not to keep everyone else much longer. Because Pavel, you and I can definitely continue another point. But any questions, anyone?
Not from our side. Anything from the chat, Dugan?
Just some questions about is this applicable to urinary operations?
To what? Sorry, applicable to what?
To single arity operations.
Unary.
Urinary.
Urinary operations. No.
Well, that's interesting. As a comment, my intuition is that this is going to sound very weird, but the Jacobi identity, I mean, you have binary Jacobi, which is traditional Jacobi, you have ternary Jacobi, which is this Filipov stuff and so on, and you can always make it bigger, right? But the question is what happens when you go one step below binary, so unary. So my intuition is that unary Jacobi is complex structure. So you square to -1. That would be my version of unary Jacobi. So it's an operation. I mean, a unary operator is an operation, right? It just takes an element and gives you another element. It's just it's an operator, right? It just operates on elements. I would say my candidate for a unary Jacobi is the complex structure, the complex identity, right? The imaginary identity. That's what I want to say. Complex structure in a geometric sense. So you have a square to -1. That would be my candidate for a unary one.
Got it.
So I would think that if it happens that this sequence of operations satisfies some mutual relations, for instance, like in the case of L infinity or something like this, that there are some mutual relations. And now also there is another actual direction which I also proposed in this Wolfram Winter School project sheet, that one can also consider actually also relations which contain more than two operations, like multiple relations.
Yeah.
And if we find something like this, then it sometimes happens that these structures admit some kind of unary extensions where something. So, for instance, in the case of L infinity, this would be called like curved L infinity or something like this, which is spoiling some relations which one expects. But it's possible that there is some operation, but it's not going to be defined in this way. It's going to be defined by some extra input, extra thing. It's not going to be defined in the way of gluing things together, because there is you need at least two things to glue them together. I mean, another thing you can consider self-gluing in a way. That's also a question. If self-gluing is defined, defined through another operation.
Definitely. Yeah. I mean, rewriting itself on a single graph, right? A single hypergraph. Any confluent process of rewriting, or even a single step rewrite can be considered a unary operation as well. Right? So maybe that way. But yeah, by the way, so in case my response to the unary Jacobi identity or application to unaries was a bit alien, my argument is that you have the way that you understand Lie algebras in 3D geometry, right, is this infinitesimal rotations, right? So the cross product Lie algebra, and that operation is understood as the oriented orthogonal complement, right? So you take two vectors, and if they are linearly independent, they span a plane, and you take the unique positively oriented vector in the orthogonal direction to that plane that completes the volume of the area, right? So so if you do that in higher dimensions, that's very easy to visualize, because you're just adding more dimensions to that codimension 1 plane where your n-1 vectors live. But if you go to 1 dimension lower, so to two real dimensions, then what you have is 1 dimension that is codimension 1, right? Because you only have 2 dimensions. So the procedure basically says, hey, you need to specify a set of vectors that have a codimension 1 span. That's just 1 vector. And so what is the codimension? The orthogonal codimension is just rotate 90 degrees, right? Like just become perpendicular. So that's exactly what the complex structure does, right? It rotates 90 degrees. And so that weird thing, square to the -1, which is like mind blowing. It's like, how could that be possible? It just means that, you know, when you're in 2D and you rotate 90 degrees, when you do that twice, you don't come back to 1, you come back to -1. You come back to pointing backwards in your original direction, right? So, and it so happens that when you are in 3D, your orthogonal complement algebra, the cross product algebra, as commonly known, is a Lie algebra. In 4D, your orthogonal complement algebra is a Filipov algebra. In 5D, 6D, etc., they are all Filipov algebras. It's easy to check. So, you know, by extension, I would just call the complex numbers also a Filipov algebra of dimension 2, right? And that's why I would claim that the algebraic property of the complex, of the imaginary unit, which is what makes complex numbers their thing, you know, do their thing. I would call that the Jacobi identity for a unary operation. It's a bit of a stretch, I understand, but it you know, it's well funded. It's not just, oh yeah, I decided to say let's do, you know, square to -1 just randomly. But yeah, very cool conversations here. Very happy to have seen this, Pavel.
Yeah, definitely a tour de force of, you know, symbolic computation.
Yep, definitely. Yeah, very good job. That was amazing. I'd love to see our Packlet being used in such a useful and powerful way. That was beautiful.
Building classical algebra on top of that.
Yeah, absolutely beautiful. That was poetry to my eyes. All right, everyone. So I think we'll leave it here today. We'll see you soon in another seminar. Thanks, everyone.
Thank you, Pavel.
Thank you. Hey.
Thank you very much. See you.